Hey guys, Mr. Betts here. I want to introduce you to an idea of linear partial fractions. This is a pre-calculus idea that we will use later on to help us with some calculus stuff. But for now, we're just going to look at the algebra of this, so no calculus involved. And so what we're going to be doing is something called partial fraction decomposition. And the idea here is rather than having two terms, two rational functions that we combine by getting a common denominator to get a single rational function, the idea here is that we're going to work backwards. So it's the reverse process of adding rational functions. So if you think about the process that we would go from this expression to this expression, we would get a common denominator, which is going to be x plus 2 times x minus 1. We combine the two fractions with the common denominators, and then we simplify. So what we're trying to do now is reverse that process. So we're going to take an expression that looks like this, and we want to go back to an expression that has what's called linear partial fractions. So linear refers to the denominators here being linear expressions, so first degree expressions. It is possible to do this with expressions that are a greater degree than linear. We will not be doing them, but it is a process that might be used in a more advanced calculus class for the purpose of helping to do calculus on more advanced expressions. So what I want to do here is go through the process of how we would do this, how we would work backwards. And the idea here is we want to figure out what the denominators of the two fractions would be. And then we're going to just put variables in the numerator and figure out what those variables would have to be. So first thing I'm going to do here is I'm going to factor the denominator. So the denominator is going to be x plus 2 times x minus 1, which tells me then that the two fractions that we're going to add together are going to have these two factors as denominators. So one of them is going to have x plus 2 in the denominator. The other one's going to have x minus 1 in the denominator. It doesn't matter which one goes first or second. Remember, the commutative property says we can do things in either order. But what we want to do now is figure out what's going to go in the numerator. The nice thing about linear partial fractions is that when the denominator is first degree, the numerator is going to be 1 degree less than that, which is just going to be a constant, just a number. So first degree, 1 degree less is going to be a 0 degree, which is a number. So what I'm going to do, typically with these problems, we'll use capital letters for our variables. And I'm just going to say A is the number that goes in the numerator here. B is the number that goes in the numerator here. Now at this point, I'm actually going to go from this expression back to getting a common denominator and get an expression that looks like the original one. So the common denominator here, what I'm going to do is multiply by x minus 1 times x minus 1 in the first one, and x plus 2 over x plus 2 in the second one. So what we end up with then is a times x minus 1 plus b times x minus 2 all over x plus 2 times x minus 1, which is x squared plus x minus 2. Okay, this should be a plus 2 here, sorry. Okay, so what I want to point out now is that this original expression here and the expression that we have here are in a very similar form. The denominators are the same, and we do know they have to be equal to each other because of the algebra we've done, which means that if the denominators are the same and they're equal, then the numerators also have to be the same. So 5x plus 1 is going to have to equal this expression here. So this is not a step I would normally do. This is a step that I'm going to write out, but normally you could just kind of do it in your head. But what we're thinking here now is that 5x plus 1 is going to be equal to a times x minus 1 plus b times x plus 2. Okay, so again, the numerator here equal to the numerator here. With that, now we have an equation where we can solve for a and b. And at first it may seem like an impossible task because we have one equation and we have 3 variables. However, this equation should be true no matter what x value we put in. So for any x value we put in, this equation needs to be true. And because of that, what we can do is just pick an x value, plug it in for x, and then use that to solve for a and b. And more specifically, we can choose convenient values of x so that we can make this equation simple and make it easy to solve. So what I'm going to do here is I'm going to choose a value for x that's going to make that first term equal to 0. So if we choose x equals 1, then this right here is going to be 0, and that's going to make it really easy to solve for b. So when we plug 1 in for x, we're going to have 5 times 1 plus 1 is equal to a times 0 plus b times 3. Okay, so I plugged 1 in for x. I get this equation right here, and the a times 0 is gone. So we have 6 equals 3b, and we get b equals 2. So that tells me then that this right here has to be a 2. Okay, now we're going to choose a convenient value of x here, specifically x equals negative 2. So we have 5 times negative 2 plus 1 is equal to a times negative 3 plus b times 0. Okay, so by choosing x equals negative 2, now this term is going to go away, and it's going to make it easy to solve for a. So we have negative 9 equals negative 3a, and we have a equals 3. So after all of that, what we can do now is we can take these two values that we got for a and b and plug it into this expression right here. And so just to be complete, I'm going to write out what we started with, and that's going to equal a over x plus 2 plus b over x minus 1. And so this is the linear partial fraction decomposition, kind of a fancy term there, but basically the decomposition, meaning we split that expression up into two separate terms, and so that's what we get. Now, right now, this is all we're going to do with it. Later on, we're going to use this to do something with integral calculus, but we don't need to do that just yet.